I admit it, I got it wrong. During our Coding at the Speed of Thought sessions, we took a look at a number of different games and how to implement them and how to improve our coding practice, our ability to model things using tools like Python, as well as our iteration practice. There was a bonus session, and in the bonus session, we live coded the game of Uno, but I got it wrong. And today, we're going to take a look at where I got it wrong, why I got it wrong, and what I believe to be the right answer. But first, I want to share with you what the answer that we were able to come up with, live coding, for our Uno look like. First, I'll run the code because, you know what? How bad can the code really be if it actually runs and works and plays the game of Uno? And here you can see we have a number of different players who are playing the game of Uno. They're either drawing or playing cards. And there's even a strategy involved where they try and pick the nearest matching card they can. And if there is no card, then they draw or they use one of their wild cards. And it seems like this seems to work. We're managing to play the game. If we speed this up a little bit, we'll even see that one player will eventually win the game. If we look at this code, there is a lot going on. And there's a lot going on with regards to the use of object orientation. Here you can see we have some enums, we have some boilerplate elimination tools, like this enum being built into this data class. We have the idea that the matching isn't done with an EQ. That's provided for other purposes, for example, to make sure that if we put these cards into a set, we get the unique values, but we have a separate matcher, because if you know the game of Uno, you match on specifically the color or special rules relating to whether it's a wild card or not, and that's going to be different than what an EQ means. And we have these two coroutines, one that loops over something and one that gives you the Uno-based ordering, including the Uno-based rules of when somebody plays a reverse card, the ordering goes in the other direction. When somebody plays a skip card, the ordering skips over somebody. And if we were to extract these two components, this is largely how we have modeled our game of Uno. The general idea for the use of a coroutine here is, can we take the idea of the ordering of the game of Uno and extract it from our main body of logic? And do this in such a way that we can test these pieces independently. So, for example, if I do loop of some entities, I should be able to go through this structure by doing next operations on it. And you can see I can get through these values. You can see here it loops over. That's going to be relatively easy for me to test, especially with a property test. And you can see it even has a flag rev for reverse. This indicates that I'm going to go into the reverse direction. So here, if I send in a non-none value or a non-false value, you can see now it's operating in the reverse direction 1, 3, 2 instead of 1, 2, 3. And then we have one more coroutine that represents the ordering of the game, and it's just interacting with our underlying looper in order to say, by the way, if it happens to be a reverse card, go the reverse. If it happens to be a skip card, skip over. And you can imagine this is also relatively easy for us to test because we could stack the deck with certain cards and then see how that plays out, and we could test an actual against an expected relatively easily or even come up with a property test. The problem here is, first, when we're dealing with these pumped coroutines that can't send the non-none value to a just started coroutine or just started generator, leads to code that's a little bit hard for us to reason about the ordering of these items. And there's a couple of small details of this that we don't like. For example, here the value that we're sending back into the coroutine is a true or false value. So we handle the looping and the direction of the looping in this coroutine here, but we handle the skipping here. And the information that we pass into the second coroutine has to be this rich object, so we really need to know what that's going to be. We need to specify that this thing works with these particular tagged values, these particular enum values. But you can think that that loses some generality. And as we try and think, how do we make this more general so that somebody doesn't have to import a bunch of stuff just to use this, we'd think that do you pass in a true, do you pass in a false, do you pass in a string, do you pass in a tuple of a true and a false? And that just becomes harder and harder for us to reason about. But there's a deeper flaw, and the deeper flaw is in how we're thinking about this idea of an iteration helper. And surprisingly enough, it is a flaw that we were already aware of. It was a mistake that we already know to avoid. Let me show you what I mean. It is very commonly the case that in Python we'll use generators in order to model any sort of computation that can be broken down into parts, any sort of ordering or sequencing of operations. And so here you can see a basic generator that just loops over a value over and over. This is the equivalent of itertools cycle or itertools repeat. If we wanted to make this an itertools.cycle, then we would just say that this is, say, the values. And we would just say for value in values, yield this, or even do a yield from values in a loop. But whatever the case may be, these are largely fairly similar. Now, if it's the case that this generator instance has been captured as a reference somewhere else in our program, for example, we have some game class, and this game class takes in an ordering, and this represents the state of a running game. Well, if we wanted to change that ordering, for example, we wanted to reverse it, we'd have to actually mutate the computation here. We'd actually have to tell the computation to do something differently. We couldn't just say, oh, hey, swap out this loop with a new looped value. And so we come up with a very simple formulation for a coroutine where we pass some data back in. And here we have typical formulation of a coroutine. Let's make sure that we get this right here, where we can send in values. If we do a next, it just repeats the previously sent in value. Otherwise, if we do a send, it repeats that value. And here we can think this is the equivalent of a looper where we can pass more data back in. Now, this is maybe a little bit undesirable in the sense that here, what if we wanted to loop over a none value? We might need to indicate what the sentinel is because we have to distinguish between what you pass back in, if you intended that to be something that we're going to loop over, and the implicit none that is passed back in via that next call. So here we might need to specify the sentinel. And what I don't quite like about it is that we may not know what the sentinel is as of the point where we're interacting with this entity. So we might actually need to send in something a little bit more structured so we can affirmatively distinguish between, is this something that you want me to loop over, or do you want me to keep looping over the previous values? There is this risk of ambiguity because next is the same thing as sending a none. So we always have to try and figure out what to do there. But for the most part, I think this is fine. However, when we first introduced the idea of iteration helpers in our intro courses, we often introduce it from the perspective of things like zip and enumerate. And we say that iteration helpers are not just a special case. You have zip and enumerate in the built-ins and that's it. But rather, they're part of a larger pattern. And the way to introduce them is when we're talking about, for example, parsing some sort of CSV data, a very common operation that even somebody new to Python might do. Here we have a little bit of code that loops over some CSV data here and is going to process it. It's going to collect all the values. Now, I want to collect these values as string values for the name and numeric values for the actual value. So I'm going to want to do an int value in here. But this blows up in our face. And the reason it blows up in our face is this CSV file has a header line. And our goal here is to think, how do we skip that header? Now, the mechanical approach that somebody would take, especially somebody who is not familiar with the idea of iteration helpers or not particularly familiar with Python, would look something like this. They'd have some loop state called line number. They'd say if the line number is 0, skip over this line, so skip over the header line, then go through everything and then update that loop state, increment the line number to 1, and we avoid this error of accidentally trying to turn the word value into an integer, accidentally trying to parse that header line. But we've traded for another bug, and the other bug is we didn't seem to process any data. And it may take you a moment to spot the bug. Well, the nature of this bug is we need to increment this line number in both of the two branches here in order for this to work. And this shows us a little bit how clumsy managing loop state is. That loop state interferes with the logic in this body in the sense that when we try and look through this body, there's the meat of the code, the thing that it's doing that's interesting, and then there's all the mechanics supporting the looping. And it's beginning to be the case that the mechanics supporting the looping are really drowning out the meat of what we want to do. From there, we introduce people to the idea of enumerate in the built-ins. And this is a problem that is very nicely solved with enumerate. We can just enumerate over the lines. We can even say enumerate start with counting from 1. And if we're at line number 1, continue. And we don't need to manage that loop state more directly so that more of the body of this code can be focused on the actual task we're trying to perform, the data processing. When we do this, we say, well, this shows you how enumerate is useful. can we do something that's a little bit more general? Can we generalize this pattern of iteration helpers? Some tool that is used to help us with an iteration by supplementing, filtering, transforming the thing that you're iterating over with some additional data, or removing some elements, or maybe even inserting some elements, although that's fairly rare, or transforming the elements that you're looking at. And we present them with an idea of an iteration helper called skip headers. In skip headers, we go through each one of the lines, and we just yield out the fields if the line number is not equal to 1. And so this code becomes even slimmer. And we imagine that this will be in some util library that everybody uses for their project. And so in general, anytime somebody wants to use this code, they're only going to have to look at something like this. We ask people, what do you think of this? Now, when I look at this code, I say, you know what? This is the idea of an iteration helper. Instead of performing some stateful mechanics of the iteration inside the for loop, we move that out into some helper, and we operate on that helper. Except we have robbed ourselves of an important modality here. Specifically, how do I know that I always want to skip this thing? Additionally, there are some hidden modalities related to the input. How do I know that the headers are just the very first line of this file? What if there are two header lines? What if, for whatever reason, somebody decided to, and we'll just make sure that this parses, do something like that? Well, for multiple headers, we could do something like max line number, and we could say, okay, as long as you are less than or equal to max line number, then skip over that. And I guess this would mean that we would look at two lines here. We'd say the max line number equals 2. But what if the headers, what if this file contains multiple CSV files? We've seen this before. What if there is some other header-like thing that we want to avoid that's not strictly just the line number? There's all of these things that we can imagine could happen to this code. And as we add more logic here, it is clearly the case that all of that logic for identifying what the headers are really heuristics. We don't know affirmatively that the header always appears in a particular fashion. Instead, we have a typical heuristic. It's usually at the very top of the file. It's usually something that parses properly in terms of the comma splitting. It's usually something that is contiguous, and so forth and so on. And by virtue of this being a heuristic, it's not certain that we can always just skip those header lines. Maybe we want to say, well, I think this is a header, maybe skip it. Or I think this is a header, except in this one circumstance it's not, so don't skip it. There's a lot more that we want to do. So instead of writing skip headers, our suggestion is write mark headers. Typically, iteration helpers should not do the action. They should just supplement the iteration with a little bit more information to guide you to doing the action. And you should preserve the ability or the flexibility that you need for what action you actually want to perform, those modalities, at the superficial most level, because it's very likely that that's going to change. If this file has some other heuristic for determining what a header is, that's likely to change at the superficial most level. If you want to keep or throw away that headers, that's also something that's likely to change at the superficial most level. Consider, you might want to debug what the header lines that you're skipping are. You might want to actually read in the header lines and use those to form, for example, a dictionary or a name tuple from the entries in this file. And so instead, we retain these two lines of code that are choosing what to do with these header lines, and we just set up our mark headers to mark the headers with this heuristic, which means we can then expand this very nicely if we have additional heuristics for what constitutes a header beyond just that it's in one of these initial line numbers. We could easily add in those heuristics here, or we could pack this into a deeper structure with all of the things that we think might make this a header line, all of that logic. And then in here, we could say if any of our isHeader heuristics match, skip it. Or if any of our header heuristics match, but also we're not happening to look at one particular file, ignore that last heuristic match because that one doesn't match for our file. We can still make use of this code, and this code is actually fairly general. When you look at this, if this thing looks similar to something that we've shown you many times over and over and over, the idea of NY's first and last, where we take an iteration and we supplement that iteration with information like, are we at the beginning of this iteration or are we at the end of this iteration? And preserve the ability to do whatever we want to do with that information in the core loop of the code, in the actual for loop itself. Well, that's exactly the idea that we're evolving towards. And so with that said, I revisited the UNO problem to see if I could implement that in a way that would better fit into what we already know about how to write iteration helpers. Let's take a look. Well, I started by trying to think, can I take the cycling mechanism and instead of choosing whether we're going forwards or backwards, couldn't I create two conjoined iterators? And one of the iterators goes forward and one of them goes backwards, but they're conjoined on some state. So instead of you deciding whether to go forwards or backwards deep inside this coroutine, you instead decide at the surface level which of the two iterators you want to pull a value from. And this idea of multiple conjoined iterators on a particular state is not too uncommon. You may have seen code where they do an iter and then they operate on that iter object so that they can maintain the state of the iteration. They don't revisit items later on. Or you may even have seen people do things like a T and they read from either side of the T in two different places. You can think that's a very simple job queuing mechanism. If you took some generator and you did T, 1, 2, 3, and then passed those T's objects to different threads, each one of them just doing a next pulls a job off of that queue. So very simple modeling of something like that. So I thought about this, and I thought about, well, there's a lot of stuff that I have to worry about in the modeling of a bidirectional cycling. This is why the name is bidi cycle. Just in trying to return something that advances through the bidirectional cycling or retreats through the bidirectional cycling, as well as something that deals with the very first case, actually starting this cycling. The reason is you can think that advance means move forward, reverse means move back, but you kind of have to deal with that modality of we're looking at the very first element, which is usually the 0th element, and then you decide if you go forward or back. Otherwise, it makes some of the tests look a little bit wonky. There's a lot going on here. I don't like how this advance and this retreat don't seem to be particularly parallel. And you can see there's a very strange flag here, allow materialize, that has to be passed in at the beginning. Because if you're going in reverse order and the thing that you're cycling over is infinite, once you reverse past the 0th element, well, you have to go all the way out to the back element. Well, if it's not infinite, but practically infinite, or just very, very large, you might want to not materialize all the elements in between, because either that could not terminate, or that could just use up way too much memory. So we add in a flag here to say, you know what, am I going to allow this to cycle past before the beginning and potentially allocate a lot of memory, which is something which hopefully the caller is able to know up front. And that adds a lot of additional complexity here. I didn't quite like this answer, so I went back to the drawing board and I thought deeply about the idea of iteration helpers. They should be simple and they should just supplement an iteration with some additional information. And I thought about what I'm basing this off of, the iteration helper of a count. Well, what I thought was, why don't we just start with count and make bidi count? We'll make a count that either moves forward or backwards from some starting point. And so here is bidi count. We have some starting point just like the itertools.count. Advance just increments the count. Retreat just decrements the count, and they're just pulling this count from their dereferenced scope. So these two iterators are conjoined with each other. Now, the return value here is the first value, because I still do think we want to preserve that first modality, and then something that we can unpack to get the advance side of this and the retreat side of this. Or, for example, if we choose not to unpack that, we could just take some name tuple and just do a dot advance or dot retreat, just to keep our namespace a little bit cleaner. The idea of actually loading elements out of some potentially infinite generator seemed to be a completely separate problem. And I implemented a very simple lazy loader. And the lazy loader just takes something that you can iterate over and allows you to get items on that thing you can iterate over, or to do standard iter and next on those elements. And if you try and ask for an element that is in the fourth of the structure, and you've only materialized the first two, it'll just materialize everything in between. Similarly, if you do negative, it'll actually materialize the whole thing. So lazy load is just the idea of lazily loading something that may or may not be finite through the get item syntax. And again, this actually seems to be much simpler when you look through it than when it was conjoined together with the looping behavior in the previous variation. In fact, my proof of it being simpler is that I was able to write some very, very nice tests very quickly from this. Here you can see part of my test case, which is defining some strategies of either moving forward or backwards, and then building from that things like permutations of those strategies, as well as masks of those strategies. Here is my test for my bidi count. I just see if I start at the right value. That's a good test. I just advance some number of times and then retreat some number of times, and I see if I got back to where I started. That's a great hypothesis test. Or I advance and then I retreat, advance then I retreat, advance then I retreat, and make sure I didn't go anywhere. That's another great simple test. Beyond that, I can even do some really fancy things taking those paths that I said. For example, I can run through one of those paths and I can see, because this thing just returns some counts, is the count just equal to the sum of plus ones for each advancement, minus ones for each retreat? And do I get to the value that I expect? And do I end at the value that I expect, and do I start at the value I expect? Similarly, I can take an arbitrary permutation, and I can see, does a permutation, or does every possible, or does some number of permutations of this get to the same point? Because you can think, advance, advance, retreat should be the same thing as retreat, advance, advance. They should all end up in the same place. And so I can look at permutations of this, and that's another great test. And finally, I can even mask out parts of the past. Advance, advance, retreat. Masking out the middle advance should be the same thing as advance, retreat, and then doing the advance that you masked out at the very end. So we can see that this is decomposable, another simple test. Similarly, for the lazy load, I can write some very simple tests of just making sure that for some concrete iterable or some abstract iterable, can I actually index this thing past? Can I index it forward? Can I index it backwards? Do I get the same result? Do I see any difference if I add in some extra indices or remove some indices? If I index all the way to the end, does it materialize everything? And so forth and so on. And I end up with some very, very small helpers. These very small helpers, I anticipate, should build out our game quite easily, because here you can see an example of our Uno logic. We set up our players, which may or may not be finite. We construct our advance and retreat counts. And you can see here one variation of this hid this behind an unnecessary extra layer of indirection. I don't believe that's actually necessary anymore. And here we have something that advances through the players. I can actually map the indices that I get to the elements I want on the outside. Thus, I don't have to worry about the count materializing or not materializing things. I could even use my lazy loader if this is non-finite or if this is abstract. If this is something like x for x in Alice, I could just do a lazy loaded of players like this, and it'll still work. And this choice of do I materialize this as finite or infinite? Well, because I control the actual access to the entities on the outside, I can do anything fancy that I want. For example, choose not to do that in some circumstances, choose to do it in other circumstances, look around at the state of the program and decide, maybe let's not do that. We're going to run out of memory. I can manage the state of the game. Is somebody skipped? Is somebody out of the game? By just having a simple dictionary here that represents are the players active or not. And if we had cards like this, I can manage the state of the ordering of the game by just saying, if somebody played a reverse card, start reading from the retreat end, not the advance end. If somebody played a skip card, just do a next on the ordering. If somebody played a skip 2 card, just do 2 nexts. And you can imagine that this here can be put into our game ordering structure together with our players. We might not even need to have the players visible in the game ordering coroutine. Here, this just has to be some indexing of activity. So we could just say, we could make this lazy so we could still do what our ideal is, which is an infinite number of players playing the game of Uno with all of the pieces still working. And here we could do something like Uno ordering. And then we can have this be something a little bit more specific to the Uno ordering. For example, referring to different card values that we've created, different card objects that we've created. And with that, we should be able to map out our entire game of Uno together with some of the object-oriented work that we've done before. Here you can see we've started this game. We've set up all of our special cards. We have all of our players set up, Alice, Bob, and Charlie. We've shuffled the deck. We've dealt 7 cards to every player. We have the pile of cards that the players are going to draw from. And all that's missing is for us to actually implement the logic of how we read from the players. Here's what I would like to do at this point. I'm going to leave this code unimplemented. Let me fix 1 or 2 other small typos in this code. But I'm going to leave this code unimplemented. And the notes for this session will be shared with you over Discord. They're on our course notes page, seminar.notes.dtc.io. I'd like if you could try to make use of our biddy count and lazy load to implement the game of Uno and to compare it against the first version that we have and to see whether we have genuinely made an improvement here. I think we have. I think we've made an improvement because we've preserved all of the modalities in the main game loop so that, for example, if we have special rules, then we can easily implement them. Here's an example of a special rule. When I play this game with Cameron, if he's skipped 3 turns in a row, he just feels very hopeless. He feels like he'll never win. He might even start to cry a little bit. And we'll just say, you know what, you can't play 3 skip cards on Cameron in a row, or 3 skip 2 cards, or a card like that on Cameron in a row, because we need to be sensitive to how he likes to play this game. And so we could add in some special handling for that very easily. It would appear just in our main game loop. Why is that relevant, and why is this problem interesting in the first place? Well, consider. Anytime we're talking about modeling a game, we're really talking about the different ways in which we might model entities which, in this case, are related to the game of Uno, but in another case may be related to any actual real-world problem. A lot of real-world problems come down to how do we sequence events, or how do we control how some machine, some state machine, moves through some sequencing of operations. Similarly, the idea of house rules and the idea of preserving your modalities is all about what happens when that one user comes to me and says, if you don't implement this feature, I'm going to burst into tears, or I'm going to be unhappy and maybe I won't buy your product. Well, whatever the case may be, the house rules are how we think about how we might deal with strange requirements coming from our end users, where to them they may seem like very reasonable requirements, but to us they may be very difficult. And preserving all of our modalities at the superficial most level is our way to make it easy for us to implement any arbitrary house rule. For example, maybe Cameron gets dealt 2 wildcards at the beginning just to even up the game, or maybe we have a rule where you can't play 2 wildcards in a row. Whatever the case may be, we could implement all of these at the superficial level, reusing all of our code without ever having to change those 2 iteration helpers that we've created. This, I think, is the mark of good iteration helpers and the mark of good reusable code, when you never have to change it, when you write it once, you test it once, and it just sits there forever solving everybody's problems. Take a look and see if you can implement the game of Uno using the pieces that I've given you. I'd love to see what you come up with, and I'd love to see if maybe you have some thoughts on how to improve either our tests or our iteration helpers themselves. We will look at the topic of iteration helpers in the near future, when we'll return to our goal of rewriting the itertools module to handle all sorts of crazy things like pumped coroutines and maybe even pumped asynchronous generator coroutines. But whatever the case may be, think about iteration helpers, think about how you can better use your code, and of course, have fun. Thank you all for joining us for this session, and we'll see you all next time.